we have defined entropy in some sense, but we'll also look at a few other definitions of it. So what we discussed earlier also is that from the first law, what we saw is that dE is del Q minus del W. So we saw that cyclic integral of del Q is equal to cyclic integral of del W, and the difference between del Q and del W for a process is what we call as dE. Of course, for a cyclic process it would be 0. This is what we saw from the first law. From the second law, what we saw is that the cyclic integral of del Q by T is essentially 0 for a reversible process, and for a general process we said that ds for the reversible process is equal to del Q by T. So we got some change in some quantity here when looking at heat and work in the first law. We called that an energy, and we got some change in quantity here, some property which we got when looking at reversible processes involving heat transfer and temperature, and we call that as ds. So we got both of them in a similar fashion, but what we do see is that we are a lot more comfortable using the word energy than using the term entropy, simply because we use it very commonly in a lot of contexts which are not necessarily very technical. Entropy itself, as given by this formula, is defined as the ratio of the heat transfer to the temperature at which it occurs, of course, for a reversible process. But what we can see is that we can use this term actually in a lot of everyday events as well. And one of the reasons we are not very familiar with it is because we do not use it. And if we were to use it in the same way in which we use energy, in a similar fashion, we would be obviously a lot more comfortable with it. What we do see is that we know that wherever there is friction, the entropy increases. So if you rub your hands, the entropy of the universe increases. If you cool coffee by keeping it out in the atmosphere, we know the entropy increases. If you make ice cream by putting ice in milk and churning it, the entropy increases, and so on. When I'm talking now, the entropy increases. When you're looking at the screen, the entropy increases. Your computer or your phone is on and running, it increases the entropy, and so on. So what we see is that practically any real process leads to an increase in entropy. The general objective, as far as thermodynamics is concerned, is that we are usually trying to make devices which have higher and higher efficiencies. What this means is that we are trying to achieve some goal where we want some conversion of some energy into some other form, or lifting of a weight or something like that. But in all of these processes, what we are trying to do is to do this process with a smaller total increase in entropy, because what we see is that the process is most efficient if the increase in entropy is small. We have seen that the most ideal processes are reversible, where the increase in entropy is essentially, for the cycle, 0. For a process, it is small. For the cycle anyway, it is 0, but for the process, we want the increase in entropy to be small. So our general objective here is to do things with a small total increase in entropy, considering both the system and its surroundings. But we can also define entropy in other forms, and in statistical thermodynamics, we define it in terms of probability. So what we see is that the net increase in entropy that occurs during an irreversible process can be associated with a change of state from a less probable state to a more probable state. That is something which we can see. That's how we define it, and we look at a little bit more in detail, though we are not going to go too much in detail. We look at one or two aspects of it. So here S is defined, entropy is defined as k ln of W, where k is the Boltzmann constant. You remember the Avogadro's number and the universal gas constant, and which gives you the Boltzmann constant. And W is the thermodynamic probability, which is the number of possible configurations. So we look at one little example of this so that we get a little better understanding. But this definition is especially useful when you want to look at things like, for example, piercing of a membrane and so on. We have, for example, over here a box. This box contains gas on one side, there's a partition here, and this vacuum on the other side. And let us say we remove this partition. The gas molecules are in motion, and each molecule can be either on the left of this partition or on the right of this partition. And you have a large number of molecules, and each of those molecules can be either on the left or the right. So what we see is that this process, we have looked at this earlier. So supposing you had, for example, this system as insulated, what we see is there is no work done. There is no heat transfer because we insulate it, which means that the internal energy of the system is constant. We have seen earlier that this system is not moving. If you take this entire box, it is fixed. There is no change in potential and kinetic energy. So any change in energy is only change in internal energy. And the internal energy is constant because there is no work done and there is no heat transfer. But as far as entropy is concerned, what we see is, what is the probability that all the molecules, when they are moving, will remain only on this side? And what is the probability that the molecules, some of them at least, will be on the other side? So what we see is that there is a lot more probability that the molecules will, any molecule will be on either side, especially if the two parts are in equal halves and the molecule is moving randomly. It can be either on the left or on the right, which means that a state where the molecules are spread out over the entire volume has a higher entropy compared to a state where all the molecules are on one half of it with the partition removed. Therefore, what we expect is that the molecules will be spread out, and this will be a spontaneous process because it involves an increase in entropy when the molecules going from one side to the other and occupying the entire volume. So therefore, we see that this kind of unrestrained expansion is a highly irreversible process, and it is something which is spontaneously expected to happen. We can also look at mixing of gases in a similar fashion. So for example, if I have a box, a similar box, I had nitrogen on one side and oxygen on the other side. I had a partition. Let's say they are equal in volume. I remove the partition. You can think of each of these gases as mixing, as going from this volume to the full volume. And the molecules are free to move. So the question is, what is the probability of finding all of the nitrogen molecules only on one side versus them being on both sides when they are free to move? And so it is in some sense unrestrained expansion of each gas into the complete volume. And therefore what we see is that this also would be a spontaneous process. It would be a highly irreversible process in which a molecule from here goes to the other side. And now if I want to separate out the molecules again and make them in the fashion in which they are now, I need to do a lot of work because I need to catch every molecule from here and push it back to one side. So that would take a lot of effort, and this would be a highly irreversible process when this mixing takes place. So there are a lot more configurations over here. So if I had 10 molecules initially here and 10 here, I could have these 10 spread out in several fashions over this entire volume, and therefore we see that it is a lot more common that we would find some molecules of nitrogen on this side and some oxygen on this side, rather than finding all the nitrogen on this side and all the oxygen on this side. So that is something which we see. One other way of looking at this is to look at a configuration which has only one type of energy. For example, let's say only potential energy for the moment. So I have here, for example, a house. This is the ground floor or the 0th floor, the first, second, third and fourth floor of this building. And let's say I have 4 objects. These objects have only potential energy, which means it only matters on which floor they are. And let us say initially this entire configuration has 2 units of energy. This 2 units of energy I can get in various ways. So what I am assuming is, in this entire discussion, if an object is on the ground floor, it has 0 energy. If one object is on the first floor, the total energy of the system is 1 unit. If one object is on the second floor, it has 2 units of energy. If it's on the third floor, it has 3 units, and so on. So for example, in this system over here, we see that these 3 are on the ground floor. They are in this bottommost box, the ground floor. They have 0 energy. This is on the second floor. So we have one object with 2 units of energy, 3 objects with 0 units of energy. So the total for this configuration here is essentially 2 units of energy. I can also have 2 units of energy in some other form like this. For example, I can have two objects which are on the ground floor. So this is 1 into 0 plus 1 into 0. So both these have 0 energy together. This is one object in the first floor, it has 1 unit of energy, plus one more object in the first floor which has 1 unit of energy. So 1 plus 1. So I have 2 units of energy when I have two objects in the first floor and two objects in the ground floor. So I can have either this configuration or this configuration. They are equally likely when I have this many particles. If I define the energy, if I say only this much energy is available, it can be either in this form or it can be in this form. And it gives me some amount of entropy considering these values. What I can do now is add some amount of heat. Let's say I add 2 units of heat. So now the total energy of this system becomes 4 units. Because it already had 2 units of potential energy, I am adding 2 units of heat, which is also a form of energy. So now it has a total of 4 units of energy. These 4 units of energy can be now achieved in different ways. So I can have one object which is moved to the top floor such that it has 4 units and the remaining 3 have 0 units, which is what is shown over here. So in the 0th floor, ground floor, I have 3 objects. First floor, second floor, third floor, I don't have any objects. I have one object in the 4th floor. This goes up here and that gives me a total of 4 units of energy. What I can also have is I can have 2 objects in the ground floor. I can have one object moving to the first floor and one object moving to the third floor. So one moves from here to here, this moves from here to here, and that will give me this configuration, which also has a total of 4 units of energy. So this is 2 into 0 plus 1 into 1 plus 1 into 3, which is 4. This configuration is 3 into 0 plus 0 into 1 plus 0 into 2 plus 0 into 3 plus 1 into 4, which is 4. And similarly, I can have cases where I have these 2 objects which are there on the ground floor giving me 0 units of energy. And these 2 over here can move up 1 floor, go to the second floor, and they have two objects in the second floor, which is 4 units of energy. Or I can have one in the ground floor, I have 2 in the first floor, and I have one from here which moves up to the second floor, and that also gives me 4 units of energy, which is shown over here. Or what I can have is, I can have these 3 moving up and this moving down, and altogether that gives me 4 units of energy. So I can have any of these configurations, all of them add up to 4 units of energy when I have these 4 objects, which I can think of in some sense as 4 molecules later on, but it's 4 objects, it doesn't matter. But what we see is, over here, I had only 2 configurations likely, so it had some entropy. Now I have 1, 2, 3, 4, 5 configurations which can happen, all of which lead to the same 4 units of energy, and therefore the number of configurations has increased. So I've gone from a system which had only 2 configurations to a system which can have 5 different kinds of configurations, which means that my entropy now is increased. So this is essentially what we see. So we see that the entropy is the Boltzmann constant times the log of the number of configurations, or the probability of the configurations more correctly. But if I have more number of likely configurations, what I see is that I have a higher entropy over here. This was when we added heat to this system. What would happen if instead of adding 2 units of heat, if we added 2 units of work? What would that have looked like? So we can see that, so we have this initial system the way it was. So it can have, we have said that it has 2 units of energy. It can be spread out in this way or in this way. It cannot be in any other way, because for example, if these 2 were on top, then that would be 2 over here plus 3 into, this is 0, this is 1, this is 2. If I had 2 objects here, that would be 4 plus 2, which is 6, so that's not possible. So these are the only 2 configurations I can have in the initial case where I have 2 units of energy. And these are both equally likely, they have some value of entropy, which is given by S. Now if I want to do work instead of giving heat, work as we know is associated with some change in the boundary. So what I can do is, I need to do work, which means I need to change the boundary of this. I can change the boundary either horizontally or vertically. We are only considering potential energy, so changing anything horizontally doesn't change the energy at all. So if I want to increase the energy, it means what I need to do is to change the height of this building, thereby doing work. So if I want to do 2 units of boundary work, what I can do is, I can now stretch these buildings such that they become double the height compared to what they were. So when these objects are at this height, they have 0 amount of energy. When it is at this height, it had 2 units of energy. These are still on the ground, they have 0 amount of energy. It hasn't been drawn showing it exactly on the ground, but you can understand that if this was actually on the ground and I stretched it, they will remain on the ground still. So as long as they are in this box, the energy does not change. But earlier, this box represented 1 unit of energy, now it represents 2. This box represented earlier 2 units of energy, now it represents 4. So I have 3 objects which are on the ground and having 0 energy. 1 object which is now at double the distance from the ground as it was. Therefore, this now has 4 units of energy. Or what I can also have is 2 objects which are on the ground, they have 0 energy, and 2 objects which were earlier at a distance of 1 unit from the ground, but now are a distance of 2 units because this building has become double the height, and therefore this has 2 into 2, which is 4 units of energy. So what we see is that we now have still 2 configurations. The height of the building has been doubled. There are 4 units of energy in both these configurations, but we are still left with only 2 equally likely configurations. So what we see is, we had 2 configurations earlier. We did work, stretched the building, but we are still left with 2 configurations only. So the number of configurations has not changed, therefore there is no change in entropy. So what we saw is that when we added heat, the number of likely configurations went from 2 to 5 and the entropy increased. When we did work instead, the number of configurations remained the same and there is no change in entropy. So that is something which is quite interesting to note. This brings us to entropy and grades of energy. So all of us are familiar with the first law in various forms. So one of the forms in which we talk of it, which we possibly used in school and so on, we say that energy can neither be created nor destroyed, but it can be transformed from one form to another. So we say that you cannot create energy, you cannot destroy energy, but you can transform energy. At least that's what we have been generally saying. So if we have, for example, 100 joules of work, can we convert it to 100 joules of heat? This we know that we can easily do. So for example, there are various ways in which we can do. We can get, for example, 100 joules of work from a battery, run it through a resistance, and it gives, if it's a steady state, it gives out 100 joules of heat. So that's one way we can do it. Another way we can do it is, for example, rub 2 friction surfaces together. For example, I can rub my hands together and that generates heat. Whatever is the amount of heat given out, that is the amount of work I am doing. So I can do 100 joules of work to heat in this way. But the reverse question is possibly more of interest. Can we convert 100 joules of heat to 100 joules of work in a cyclic process? The first one we can do in a cyclic process, we can convert work to heat in a cyclic process. If you have, for example, a resistance heater or something like that, you can make sure that it converts it and then it comes back to its original temperature. We can do that. But can we do the reverse? So we know from the second law that this cannot be done. Because if we have 100 joules of heat and if we want to then get work out of it, what we know is that we have to reject some heat. So not all the heat is being converted to work, because some of the heat needs to be rejected as per the second law. And we saw that the maximum we can convert is based on what the Carnot engine would do, because the Carnot engine takes heat. So for example, if I give 100 joules of heat to a Carnot engine, it would do some amount of work which is based on the temperature of the high temperature and the low temperature sink, and it would give some amount of work and reject the remaining heat. So it would not, if I gave it 100 joules of heat at high temperature, it will not give me 100 joules of work, because we know the Carnot efficiency is also not 1. So this is going to be even less than this. Depending on the temperatures, it may be half or more than half or less than half. And therefore, what we see is we cannot convert all of the heat into work in a cyclic process. So therefore, we see that there is a distinction between work and heat. So both of them are forms of energy. We say energy can neither be created nor destroyed, but it can be transformed. But now we see that the transformation, there are some limits. If I want to convert work into heat, I can convert all of the work into heat. If I want to convert heat into work, I cannot convert all of the heat back into work. I can only convert some of the heat into work. So let me repeat that, because that is an interesting and important concept. So what we see is that we can run a cyclic process and convert all work into heat. But in a cyclic process, we cannot convert all heat into work. So there is a distinction between heat and work. So work is useful because we can use it either as work or we can convert it into heat. Heat is not as useful because we can use it as heat, but we cannot convert it back all into work. So we see that there is in some sense some gradation of energy. So we have some grades of energy. For example, mechanical work, potential energy, kinetic energy, electrical energy, and so on. All of these are completely convertible from one form to another. I can convert mechanical work into potential energy. What I can do is I can do work on an object, raise it and increase its potential energy. The object which is at high potential energy can get slowly lowered and do work. I can have an object which is dropping, so its potential energy is getting converted to kinetic energy. I can have an object which is thrown up and it's slowing down, its kinetic energy is getting converted into potential energy. I can convert, ideally, electrical energy into mechanical work if I don't have any resistance losses. I can convert mechanical work into electrical energy, and so on. So all of these are completely convertible, at least ideally, from one form to another, and therefore we call these as high grades of energy or high grade energy. We have, for example, chemical energy, which in some cases we can convert directly into electrical energy, but in most of the cases, if we look at, say, for example, fuels, what we see is that we cannot convert the chemical energy in the fuel directly into work. What we are typically doing is releasing that chemical energy in the form of heat and then trying to convert that heat into work. So therefore we see that in these cases we cannot have a complete conversion of whatever chemical energy is available into work. Therefore it is not as useful in some sense as, for example, mechanical work or potential energy or kinetic energy, in the sense that it is not fully convertible. And then we have heat, which is our lowest grade of energy, because what we see is anything can be converted into heat, but we cannot convert heat back into other things. So if you now recollect, right from the beginning of the course, we have been talking in some sense about energy, because thermodynamics deals with energy, but we have been classifying things as work. We spent a lot of time discussing what constitutes work, and then we spent some time discussing what constitutes heat, and then we came to the first law, where we said that work and heat are forms of energy, and essentially as far as first law is concerned, they are the same, because we can convert one to the other as far as first law is concerned, because it just means taking some terms from the left hand side, putting them to the right hand side, and everything is fine. But as far as the second law is concerned, what we see is that heat and work are not the same. So work can be converted to heat, heat cannot be completely converted to work, and therefore they are different, and this is essentially why we have been referring to them differently from the beginning of this course. So what we need to keep in mind is that work and heat behave in different ways. This also has interesting implications for all of us. So for example, if I have a tube light or a fan or a bulb on at home, what I need to keep in mind is that where did this energy come from? So if you take a country like India, we get a lot of the energy from coal, which means it was initially chemical energy which is stored, which is converted into heat energy by burning the coal, and that heat energy was converted into work. And then the work in the form of electrical energy, of course, it was initially converted to mechanical work, which is then converted to electrical energy. Then it was sent across wires to a long distance, and then it comes here. And then, for example, you have a bulb and you're converting back into heat and you're looking at it at light. So if I had a 100-watt bulb which is on here, how much heat did I need to liberate initially to get this 100 watts? That of course depends on the system which we have, on the power plant and on the transmission losses, on the generation, the efficiency of generation of electrical power and so on. So taking all of those together, if I, for example, put a number of say 30% efficiency, which is not very high but not very low either, then what we see is that in order to run a 100-watt bulb here, I must have burnt coal to give me 300 watt of heat at the power plant. So what we see is that any energy which is lost or wasted, I mean, it's not exactly lost in the sense of it is of course conserved, but it is wasted because if I am, for example, outside a room and the light is on in the room and I have this energy wasted, it is not just 100 watt of energy which is wasted, but it is 300 watts, because that is what essentially gave me this 100 watts of light in the room. So therefore it is important to make sure that we do not have electrical appliances on when we do not use it, because typically we are spending about 3 times that amount of energy initially in order to get it in some form over here, because we are trying to convert low grade into high grade energy for the purpose of transmitting it, and we are transferring that high grade energy back to low grade energy in the case of a light or a fan, because we are dissipating it, we are doing giving it out in the form of heat, or we are using it, for example, to churn the air, which then, because air has viscosity, it has friction, gets transmitted out in some form as heat later on. What we see is that we are converting low grade to high grade, which means we need to give much more low grade energy to get some amount of high grade energy. So depending on what the efficiency is, we may need to give 3 times the amount of low grade energy to get 1 unit of high grade energy or so on, and therefore we see it's not essentially a very good process. We will go on now to a reversible adiabatic process for an ideal gas.